So good morning, everybody. Let's wrap up where we were, or at least wrap up discrete time systems. So actually, I think we've covered everything about them in time domain. Discrete time systems analyzed in time domain. And of course, typically here in this course, we work with linear time invariant systems. Okay, I'm not sharing the screen, right? Let's share. All right. So wrap up discrete time systems, and typically this course mainly works on LTI systems, linear time invariant systems, but we said actually linear, nonlinear, any algorithm is a system, right? For us, actually, there is an input, there is an manipulation of the input by the algorithm, and then there is an output, right? The algorithm outputs another signal or data. So recall, for instance, this first order, the FIR filter. Remember, FIR is finite impulse response filters, and we've studied in this course those FIR filters. They have finite number of coefficients. Okay. These IIR filters typically are used in, remember I was telling you, electrical electronics engineering, and that's why actually in this course we are not really covering them, but I gave you an example last time. So for instance, first order FIR filter, we give a Yn, the IO relationship, okay, x of n minus x of n minus 1. Okay, so here, remember, what was defining an LTI system? Two important things. I mean, they are related. There is an impulse response, right? X of n goes in, and then this LTI system, remember, is actually characterized by impulse response. That's like a signal too, remember? And actually, for instance, if it's an FIR filter, this is just a filter, right? Set of filter coefficients and then output. And remember, in time domain, convolution is the operation that ties the input to the output. So it's really output is x of n convolved with h of n. So ties the input to the output through the impulse response, right? So convolve the input with the impulse response. So here, what is the impulse response? This filter, you see, is actually, you know how to find impulse response, right? Impulse response of this system. Remember, we replace x of n by delta n, right? N minus 1. Okay, so this is a filter, and you look at it, it's a filter of two coefficients, actually, 1 and minus 1, right? And this is your h of n. I want us to actually compare these two. This is a first order FIR, you know, these are common filters. This is a 1 minus 1. Now compare this to, we will see the effect of it on an input signal, but compared to, for instance, let me see, 5-point running average filter, right? This is, the IO relation is 1/5, remember, k equals 0 to 4, right? 1/5 is actually here, I mean the filter coefficient, right? X of n minus k. Doesn't matter if it's here or not, of course. X of n minus k. Here the coefficients, and what is now h of n in this case? This was a side note, so let's just. So what is h of n? The impulse response. In this case, it was 1/5, right? K again 0 to 4, of course, delta m minus k. So actually the filter coefficients are, you can see from here, 1 over 5. So let's make it 1 over 5. Let's make it like this, 1 over 5. And 5 of these, right? So for instance, now the filter coefficients, they are 0 everywhere else. Here also, this was 0, 1, 2, 3, minus 1. Now it's minus 1, 0. You see, it's non-zero over 5 values here. And actually, there is a difference here between the two forms. What are their effects on the input signal? What is the difference between them? I want you to think of it. For instance, let x of n, guys, be, for instance, I gave this input signal, x of n is given as a graph, let's say 1, 1, 5, 4, 5, 4, 0. I mean 0 is of course here actually starts from 0 index here, 3, 4, and 5. And it's 0 everywhere else. So let's say this is the input signal. Now let's see the output for both of the systems. You can do this, guys, and let's just plot the results. Y of n with the FIR filter. So let's say Y of n with this first order FIR. I mean, this is also FIR, of course. This is also FIR. These are both, let's use maybe color. This is FIR. This is also FIR, of course, right? Finite number of coefficients. This has 2 filter coefficients. This has 5 filter coefficients. But there is one more fundamental difference, I mean, between these two filters. So for instance, the effect of, let's say, okay, let's check first, effect of the RAF filter. For instance, output of the running average filter. Let's first do that. 1 over 5, guys, 2, 7, 11. I mean, it won't be to scale, so please just, I mean, I don't have enough space here. 11 over 5, I mean, these are all over 5. You can calculate it, so that's why I'm just writing it. Actually, it's more 11 over 5 here, one more. Please calculate this as an exercise. Over 5, and actually I didn't even complete it, but you can do it for, please exercise, let's say. So let's calculate the output Y of n for both filters, and given, of course, and given this x of n, okay? So this would be the first output, Y RAF. Now let's look at the first order difference FIR filter. Then that would be, this was Y RAF, this is Y first order difference, let's say n, and let's plot this guy. It's gonna have a 1 here, 2, let's say these were 0, 1, 2, 3, 4, 5. So at 1 it is 0, at 2 it is 4, 3 is minus 1, minus 4, and at 5 it is 1. So guys, can you guess what are the effects of these two filters? So maybe let's use red here. So if we look at, I think we mentioned this. What type of a filter is this? I mean, probably this will go as something like this, right? I mean, what kind of a filter is this running average filter? The name implies, right? It's a smoothing filter, right? So you see, takes the input, this is the input, right? It gets smoothed. What about this one? Okay, here it is that effect. So what about this one? Now what is happening here? This is actually difference. Actually, I should have said here first order difference filter, guys. So now the name implies it takes differences, meaning you see the other one takes sums. This takes differences, the first one. So here it's trying to detect changes in a signal. Okay, because it's taking subtracts the previous sample from the current sample, right? And it shifts itself, this filter coefficient set just slides over the input signal, right? I mean, maybe let's just remember the effect. Remember, if I have, for instance, a 1 filter, I mean, if a value of 1 and a -1 and all zeros here, this is my h of n, and bring the input here. It was, okay, 1, 1, 5, 4, for instance, let's say 1, 1, 5, 4, I think 0, 1, right? Okay, 0 and 1. What we were doing was take this guy, flip it, right? So I have to flip it. It's gonna come here as -1, 1, for instance, right? And this guy will shift over the input signal. So this was x of n. And then we multiply and sum it up. So for instance, that's how we calculated actually. I would say, hey, this sum is 1. So at y of n, I have 1. Now shift this signal, filter. This is flipped h. So this is h minus n, right? Minus k, actually, let's say. Because n minus k, for instance, I will need h of 1 minus k. So let's maybe shift it a little bit more just to see, not y of m, but h of 1 minus k. So I would need to really put the filter now at here, right? 1 and -1. So this was 0 and -1. Now this is 0 and 1. You see what I'm doing, right? So it's gonna really, now you see, I had 1, 1 here in my input signal. And this guy, when multiplied by this, will give me 0, like multiplied and integrated. So it's really doesn't see any change in the signal. That's why. Okay, that's why then the y will be 0 at that point. So from here, I can say, so maybe, okay, let's use y of 0 was 1, but from here, y of 1 was 0. Because please imagine, multiply this guy by x of n. This guy multiplies x of n. Remember, this is really sum. X of k, I mean, doesn't matter, k or x of k. Okay, this is h of k. Okay, because the shifts are n here, that's why. X of k, h of 1 minus k. Okay, and summed over all k. This is it, k. So you can do it in this way. Now shift it, h of 2 minus k. So this was n equals 1, n equals 0, n equals 2. Now shift the filter one more time. It's going to be -1 at 1, and it's going to be 1 at 2. Okay? So this is this signal. Now multiply it with the x of k. You will have y of 2 as sum k. Okay, it's okay, sum k, x of k h of 2 minus k. What do you have? You guys get minus 5, 5, 4, right? Okay, I think it's clear. This is the mechanics of convolution. Sometimes, guys, we've done it, but I just redid it. Sometimes we call it convolution, but it's like correlation. Remember, correlation is without flipping the filter. Correlation is take the, for instance, filter and swap without flipping, just again slide it over the other signal. So this is really, they are almost. So correlation is like convolution without flipping the filter, flipping that h of minus kt. So actually, guys, you know, we talk about in machine learning now CNNs, these famous CNNs, convolutional neural networks. Actually, these guys are really not flipping the filter because we're already learning the filter weights, doesn't matter, right? So that's why actually you would be, I mean, maybe you would see they are doing correlations, but really here in this case, it's like we're learning the flipped filter, doesn't matter. There is a filter there that is being slide over the image, but underlying computations could be, by the way, filtering, guys, mainly in our tools, numerical tools are done through FFT. We will see how we go to frequency domain, do a multiplication and come back. That will be, this is in frequency domain. We will see later. Computed in frequency domain, we'll see next week. So, okay, actually, let's wrap up the discrete time systems. I think we've learned all the properties. Actually, with continuous time systems, we will, some of the properties are common, so we will really go over them again. Any questions from here? You see the difference, right? This guy, the difference filter really detects abrupt changes or changes in a signal. And this guy, the 5-point RAF, smooths the signal. We've already said that here. Smooths the signal. Averages, right? So that's the, I mean, I'm trying to show you different effects you can design with filters. So I think at this point, if this is clear, if not, ask please. We could go to continuous time systems. We will do this a little bit quick. Okay, continuous time systems. This is, guys, in the, not the DSP book, but the SP first book, because DSP is digital signal processing, and the SP first book, this is more general, with it covers both continuous time and discrete time. SP first, this was chapter 9, I think. But almost everything is the same, only the delta function, we will define it now, and convolution is continuous operation actually. Other than that, many properties are same. So guys, now again, we have a system, let's say, but let's say it's a continuous time system. Okay, so this time an analog signal, a continuous time signal goes in, and a continuous time signal goes out. You see the difference, right? I mean, it was before X of n, Y of n, you know, sequences. Now it's continuous time signal input and continuous time signal output. Okay. So now what characterizes this system? By the way, what kind of systems are these? I think we've talked about this microphone example, right? Sound waves, for instance, X of t, let's say sound waves. These could be actually captured through a microphone and converted to an electrical signal, right? Let's say captured via microphone. So this could be an electrical signal representing your voice, for instance, or music in the environment. And you may be doing some manipulation in here, in between. Typically now it's actually that manipulation is digital. For us also, actually, it's mainly working in that way. I mean, for what relates to us. There is an analog to digital converter. Remember, we go to by x of nts, it is a parameters with a sampling rate. We go to a discrete time signal. We can do some discrete time processing through a system. What could happen to that music audio is up to you. You may be compressing it. You may be, for instance, changing, playing with the frequencies, increase the pitch frequencies, suppress the bass. You know, if you're a musician, you guys know these things, but it's really about, don't worry, I mean, if you're not a musician, it's really about playing with the frequencies. We will see that next time, how we can play with the frequencies. Then here, let's say maybe another thing. Okay, yeah, Y of n goes out, and then you be converted to with a discrete to analog filter system to Y of t. So this system here is really this continuous time system. Could be, for instance, something like this. Or, guys, I mean, this is the way going through the digital, right? This is digital processing. Digital signal processing, so digitized. We've been looking at this in discrete time systems, actually. Here, then, this was Y of t. But actually, there are, you guys remember these better. There are also, of course, let's say, analog systems like, for instance, circuits, right? Circuits. I mean, these are physical systems. I think we've drawn one last time. It's out of our scope, of course, but just to recall, there is a switch. For instance, this is a voltage, let's say, generator, or maybe a DC voltage. You have a capacitor C, and then I may have a resistance R, right? This is, remember we said this last time, this could be like, this is my x of t. Maybe it's not, it's an alternating current, it's a time varying current. So x of t, a signal, you can say this is the input to the system. So where you measure this voltage, and then you may be measuring an output here, right? At the resistor, for instance, or actually equivalently at the capacitor, right? But depends on the switch. This is really just an example. I mean, analogy. This is an analog signal. An electrical signal goes in. It's a continuous time signal. And another continuous time signal is at the output, right? So this is really, guys, just for you to be able to visualize, this is really a continuous time system, right? Makes sense, right? Exactly. You guys work maybe with these. I don't know at what level, but I mean, this is just an example for us. I don't know other physical systems you could think of. I think in mechanical engineering, right, there are many physical systems like spring systems and things like that, right? This is EE from EE field mechanical engineering, for instance, spring suspension systems and things like that. Okay, anyways. So this is mechanical engineering. This is EE engineering examples. These are completely analog systems. That's what I'm trying to say. Completely continuous time systems. So for us, it's mathematical. This mathematical manipulation through continuous time systems is actually to be able to probably be good with the math to understand what's happening there, because it leads to some level of abstraction for us also, you know, coming from the continuous time system. For instance, here you can, in both of these cases, in RC circuit and, for instance, a suspension system, you can write a differential equation to model the system. More physical systems actually work that way. But then we should be able to also understand, for instance, what is going in, what is going out. Then what is the, for instance, if there is there a difference equation equivalent, things like that. But don't worry, the continuous time and discrete time systems work in a very similar way, you can say. I mean, work in a similar way, meaning we study them in a similar framework. That's what I'm trying to say. And again, here we will have an impulse response. That's important. So guys, here we will have something. So we will have again an impulse response of the system. What is the impulse response and what's its goal? Remember, its goal is really actually to measure the system output. This is the input, right? To measure the system response, or it's how it behaves when it is actually perturbed with a very short duration signal. It's right. Delta is a on and off, right? In a way, think of it as a circuit, a switch. It is closed and opened. So it's really a perturbation, a small perturbation to the system. Please remember it in this way, impulse response. So we're trying to characterize an LTI, linear time invariant system. Again, through the impulse, we will define now this continuous time impulse function. Okay, measure the response of this LTI continuous time system against the input, measure response against, right? Against the input or to the input, delta of t. So this is also equivalent to perturbing the system with a infinitely short duration, right? Because it's an instance. This short duration signal. Okay, so here this is our delta. This is, you can think of like a canonical input, a standard input. We're trying to push and then obtain a response with respect to that. And we will see that this is again will be then actually, okay, sorry, this will be h of t at this point, right? We are measuring this because I'm giving delta and this is my impulse response. Okay, so then whenever an x of t is given, right, then whenever an x of t is given to this LTI system with h of t, this h of t, we know actually from the discrete time systems, right, y of t is h of t convolved with x of t. This time this will be continuous time convolution. But let's first define this delta of t. Remember, in delta discrete time, recall delta of t, or delta of n, sorry, was really very easy to define. It is equal to, guys, this was 0, of course, man. Okay. Delta n was really easy to define. It was 1 for n equals 0, and it was 0 for n not equal to 0. Here it's discrete time. It's easy to define. But what is it in delta, in continuous time? You can't really say, I have this guy here, because this is an instantaneous time point, infinitely short duration. We have to define it as a generalized function. So this is not a function. It cannot be a function in the definition of functions. It's a generalized function, and it is defined as a limit in this case, in the limit. So we will define it in the limit. In the limit. So in this way, we will say instead I have actually a rectangle, right? For instance, let's say it's a delta sub delta of t because it's, let's say it has a width delta. It's still a continuous function. Delta of t, it is equal to here 1 over delta, and its area underneath is 1. So let's say our goal will be this. This guy will be equal to 1 over delta for t between minus delta over 2 and delta over 2 and 0 else. Otherwise, okay, so this is minus delta over 2. Maybe I should do this on the next page because I want to now make delta small. You see, I said we will define it in the limit, right? We will make delta very small, take the limit and see what happens. And our goal will be to make this delta sub delta, the triangle, go to this function of delta of t. Okay, so let's see, say this is, by the way, really an interesting function. So it's actually this, guys. Let me redraw it. So I was saying, hey, I have defined this delta sub delta t, right? Minus delta over 2 to delta over 2 t, and it's really 1 over delta here. Now make delta small. For instance, let's make it half the size. You see, I'm trying to keep its area 1 because I wanted to have some mass, right? So really, then its magnitude is increasing. Okay, so here now it's minus delta over 4 to delta over 4. Now I have 1 over 2 delta. I can keep continuing and keep doing this. Okay, so let's just say, you see, I'm taking the limit or take delta to 0, right? That's our, make delta small. That's what we're doing. So in the end, you see what we have, right? Okay, by the way, delta sub t was, let's define it here, t between, maybe let's say t less equal delta over, oh, sorry, 1 over, yeah, delta over 2 in this case. And 0 otherwise. Okay, now this delta of t is defined, this is definition, as limit delta goes to 0 is delta sub t. So what properties does it have? You see, its amplitude is an infinite amplitude actually, instantaneous, but it's an infinitely short duration. That's why it doesn't blow up actually. In the end, when you take the area underneath, its area will be 1. That's the point. So let's do this. I mean, here important thing was first it's delta times 1 over delta. So the area here, important thing is infinity to infinity. For this guy, the area it was 1. Similarly, right, we wanted it to be this way. So area underneath is 1. Similarly, actually, as delta goes to 0, but we keep still delta of t, delta went to 0, and now this guy went to delta of t, this guy is also still 1. This is the property we want. So we want these rectangles, even if it becomes infinitely long. So in the end, the intuition is this. In the end, delta of t has infinite amplitude, is an infinite amplitude signal, but infinitely short duration signal. So it's really a perturbation, instantaneous perturbation, okay? Signal. Therefore, delta of t represents, mathematically represents. In continuous time, it's typically mathematical abstraction, right? Modeling. So represents, delta of t represents an instantaneous perturbation to the system or perturbation signal. And it really achieves that to our system. So let's see if there are questions here. Chat. Oh, You can't hear me or okay, so okay. Thanks. I think it's done. What are we trying to say with the sign delta above equals? This is definition. Don't worry. I mean, don't get confused. This is in mathematics. It's a notation. This means, guys, thanks for asking. It's good you asked. This is this notation. Let's just say maybe don't means defined as. Okay. This delta means. I mean, this symbol is equivalent to defined as. Yeah, please know it. It's known used in mathematics. Okay. All right. So now delta of t, we can still say actually. So delta of t has two properties. One, it is zero when delta. So we can say it is zero when t is not zero. You see, I mean, it's this signal. Typically, we mention it like this because we just try to say area underneath is 1. That is implicated by here. This is the property minus, I mean, let's rewrite it. I had it, but I mean, this is really indicating that area underneath is 1. You see, but we can't say, but we cannot say, please don't say this ever, delta of t is 1. This is wrong. At t equals 0, you can't. You see, it's really not 1. It's infinite amplitude. Its area underneath is 1. Okay? This is important. This is the third property, probably I should write. Okay. And this is also equivalent to any AB delta of t dt is 1 if AB includes the 0, of course, right? This is t. This is my delta of t. Why did we define this now? Because it helps us define, you see, the convolution of continuous time systems. It helps us sample from the signals. For instance, let's say, is this clear until here before I move on? Somewhat, at least the idea, intuition is clear. Thank you. So for instance, sampling property of the, okay, let's, sampling property, okay. Sampling property. X of t, let's say, dot, this is the first one actually, x of t dot, for instance. By the way, I can shift delta, right? Like I did before. Now this guy would be, let's say it's 0, now go to t0, and the same idea, right? Its area is 1. This would be delta t minus t0, and it's 0 everywhere else. So we know this is really 0 for t, not t0, right? Now, its area is delta t minus t0. It should really include this range. For instance, 0 to 20 t0. This would be, I know, I'm sure this would be 1, right? This integral is 1. Because I'm trying to really integrate by including t0. So this guy really samples from the signal. Let's see, for instance, just draw a continuous time signal here. Just, for instance, x of t, go to t0. For instance, this is t0. Now my delta here is a, remember, instantaneously on and off signal. So it really samples the value of x of t0 here at this point. But I also have, I'm showing, I'm multiplying it with this delta, right? I mean, here there is a delta t minus t0, right? There is a delta signal, and it's multiplying because this point is really x of t0 value. It's samples from the signal. The second sampling property is if now we integrate that out, it will just be left with xt0. So the integral kind, this was multiplicative sampling, this is integration. Minus infinity to infinity, x of t now delta t minus t0. Remember, dt of course. I use the first property because we know this is really x of t0 delta t minus t0. Then that's really x of t0 times minus infinity to infinity delta t minus t0 dt. I know this is equal to 1. So this is really, you see, extracting out the value of the signal. So samples the value of the signal at the t0 point. Then another property, guys, is so we are actually, so let's say this is the third property. Properties, we were studying properties of delta of t, right? 1, 2, 2, okay, this is not 3, this was a side to 2 or side to 1. 3, now let's go to 4 property, relation between the step function, continuous time step function, u of t and delta of t. Can you guess what was u of t? Or let's maybe do it here, show it here. Heaviside function, right? Remember, it's zeros here, and it's equal to, you know, when t is less than 0, it's all zeros, and when t is greater equal 0, let's say it's 1. Take imagine taking derivative of u of t. Or maybe before that, look at, let's say, minus infinity to t. This is also another way to delta tau d tau. I mean, just use another dummy integral variable, okay? So this would be, guys, when t is greater than equal to 0, this would be 1. But when t is less than 0, this would be 0, right? This is exactly the step function, definition of the step function. You see, integral of the delta function is, so integral of the impulse, or delta sometimes I say, is step function. This is step, right? Step function or Heaviside function. From here, we can also say the derivative. I can define the derivative of u of t as delta of t. I mean, just see the effect here. Now take the derivative d by dt. You would really end up with just this delta of t here with area 1. This is okay, delta of t. U of t to delta of t, okay? Okay, this is it. What else? Time scaling. Okay, so some properties of delta of t. These are the only differences from discrete time, actually. So let's just finish them up. Delta of t, time scaling delta t. Guys, time scaling. So remember, again, we have this guy, my delta, sub delta t. Okay, minus delta over 2, delta over 2. So now let's do, for instance, and we were really saying the limit, in the limit delta goes to 0, we had delta of t. Now look at delta of 2t, guys, or delta sub delta of 2t. Remember, this would compress the signal, right? Time scaling means, let's say, I'm looking at this guy, this would really compress it. So it would be really, right, minus delta over 4, delta over 4. You see here, this is the guy. this was 1 over delta. Again, 1 over delta, but this was the width of the signal was the delta, but here now its width is narrowed down, right? Scaled down by 2. Now, from here, the area underneath shrinks to 1 over 2, right? So area shrinks. Now, then we would have actually, let's say, this would show us this guy is really equal to 1 over 2 delta 2. Shrinks by half, let's say. And then this leads to the result here. So generalize this to any A scaling. So delta AT would be really 1 over A, but I need absolute, right? This could be also minus 2T, for instance. That's why I need this guy. For instance, from here, what is delta minus T, guys? E.g., I mean, it's symmetric, of course, delta of T, right? From the formula. Okay, so this is really time scaling of delta. And maybe I can say this as the last thing. I think we did this for discrete time signals. We can write any signal x of t as minus infinity to infinity x of tau delta t minus tau. So t minus tau d tau. Here tau is a continuous variable. Before, remember, that was a k. So we wrote any signal as, remember, some k, right? X of k, delta m minus k. Deltas shifted to those k's, right? Recall, for discrete time, we wrote any. So we can write any signal as the signal itself times the delta, shifted delta. I mean, it's easy to understand in discrete time. Continuous time is the integral version of this, actually. Integral version, in a way. I mean, here difference is, of course, k is an integer index. Here, tau is a continuous variable. So, okay. All right, so guys, these are some properties of the delta function. So, I mean, continuous time systems. Any questions until here? I know these are new to you, so they may look a little bit strange at first. Just a sec, I'll close. All right. So we were saying, can we find, for instance, the impulse response of the integrator? It's really actually straightforward, right? Insert x of t is equal to delta of t. So for instance, actually, we will have delta of tau, right? Minus infinity to t d tau. So this would be the integrator impulse response. And what is this? We've defined this actually. What is this function? This is really 0 here and 1 for all other t. This is u of t, right? So you see step function is the impulse response of the integrator. Makes sense probably, right? It's really, in a way, integrating out everything you see in the signal starting from t equals 0 is the impulse response of the integrator. For the differentiator, differentiator was y of t. Let's write its name again. Differentiator system was y of t is d by dt let's say x of t. Here's we define something. So now let x of t is delta of t, guys. H of t, then the impulse response is, you see, generalized function getting integrated. Remember, this was defined, we defined it in the limit of a delta sub delta of t, remember? This was, of course, something like this. But then imagine in your mind taking derivative of this guy, d by dt. So actually, and we were showing this guy as this integral, right? Now, when we take the derivative, it's going to be actually a positive, right? A positive derivative here and a negative derivative on the other side. But actually, these as delta go to 0, you see why I'm saying that, right? Because it's a rectangular signal, right? There is an increase here and a decrease here. I mean, that's why the differentiation derivative is a negative, a plus one and a minus one. And we show it actually, and this is defined as, again, delta first derivative of t, and shown by this, let's say, here, and also a negative one here. I know it looks a little bit strange, but this guy is the derivative of delta. Okay. So what else were we doing, guys? For instance, another system is modulator system. We will study modulation later after we cover the Fourier transform. But just to give an example, input-output relationship, for instance, A plus, or doesn't have to be A plus, but let's maybe just say A times, or X of t, let's say, X of t times cosine omega 0 t. Okay, so this is the modulator system. Remember, we mentioned this, I think, and we said this is typically a high frequency carrier signal, typically a high frequency sinusoidal. And we will see in the spectrum representation. Remember, we were doing all spectrum representation. Next week, starting in the coming weeks, we will go back to spectrum representation again. These few weeks, we are doing time domain representation. I think that's fine for some continuous time system examples. These were some, let's say that these were some continuous time system examples. Title is, I think it's better, right, to say that, because we looked at some continuous time system examples. Guys, the other properties of these continuous time systems, like linearity, time invariance, okay, the causality, stability, they are all defined in the same way. This is LTI. So I won't be defining them again. Similar to, equivalent to discrete time systems. So let's say properties. They carry over. We can do a few examples. I mean, should I, let's see, any examples of continuous time systems? I think maybe this is an interesting example. Oh, okay, maybe this guy. Example, let h of t, if I'm giving you the impulse response, and you guys will see this is really an infinite impulse response. This is for an LTI system. Okay. Is it stable, for instance? Okay, let me write the question here. Is it stable? So I want us to recall all these properties. So let me see. I had a nice table for that. Yes, the valid for all. So let's for stability and causality. I mean, LTI is, I remember, it's really superposition and this delay invariance. That's fine. This causality stability system, recall this is just a summary table. Stability. Okay. Causality. And we will look at two cases, a general system and an LTI system. Remember, we have for an LTI system, because I know h of t or h of n, right, for the discrete time characterizes the system. So I can really look at the h, the impulse response to, for instance, be able to see whether this system is stable or not. This was, remember, bounded input, bounded output stability though. There are other types of stability definitions. I assume you remember this from last time. And this general definition of bounded input, bounded output, as the name implies, every bounded input produces a bounded output. Right? Then if we can show that, prove that, we know that's a stable system. And causality only, the system only uses current and past values of the input, right? Or relies on past values of the input. Okay, but for LTI systems, remember, we were able to actually talk about these properties in terms of H. For instance, for stability of LTI systems, we have to look at absolute summability of the impulse response. Now, in the continuous case, H of t dt is finite or not. Absolute integrability in this case, of course. So this is really absolute integrability, or this is for continuous time, or summability for equivalent summability for discrete time. Okay, equivalent. What else? For instance, causality we've shown last time for discrete time systems. It's the same thing for continuous time. H of t should be 0 for t less than 0. Then I know it's a causal system. So for instance, from here, from this table, guys, from this table, for instance, h of t to the minus t u of t, this is, I can say, causal, right? And is it stable? We just have to integrate it. It looks stable to me, right? Absolute sum, exponential decay, it should be stable. You guys can show. Actually, that's a finite sum. So let's see. That's 3t. U of t is just 1, but it goes from 0 to infinity dt, right? Actually, this is less than or equal to 1 always. Bir saniye. Can I say it in this way? No, it won't be possible like that. I have to really take the integral, right? In this case, but it's already positive in this range, right? You guys would be better remembering this. It's something like this, right, guys? It looks to me absolutely summable. It's already, I think, minus 1 over 3, right? Minus to the minus 3t. P0 is 1 minus goes to 0, right? So am I right? The underneath, area underneath, is it 1 over 3? Sorry, minus 1 over 3, or no, it's minus 1 plus 0, right? So yeah, plus 1 over 3. Yeah, to me, it is stable. What do you guys say? This integral looks correct, right? Correct. I mean, this was minus 1. Okay. Stable, and it's causal. We've said that. Looking at this, example, for instance. This is EG. Okay, any questions, guys? Yes, thanks, guys. For instance, integrator system, is it stable? I can ask you. This was with an exponential term, right? E to the minus 3t u of t. But integrator system's impulse response is u of t. Example, integrator system. H of t is really the step function. But what is area underneath? Infinite, right? So that's why it's an unstable system, and actually intuitively integrator is unstable. It can blow up, right? If you keep integrating something forever, it may blow up. Here, causality, yes, for instance, but not stable. Stability, you guys can also check this, minus infinity to infinity h of t dt, and you can see this is really, okay, maybe I could say 0 to infinity 1 dt. This is not less than infinity, so it's unstable. You have to do finite sums, of course, not stable. What else? Actually, maybe let's do a convolution and see what it produces. So let's maybe do a convolution, continuous time convolution example now. And I think then we can see what this refers to. But linearity, and by the way, the LTI properties, it's the same way, proved as the same way. Remember, we were showing LTI, time invariance, show them as the same way, as in the same way we did in discrete time systems. Let me note that just for your notes, please. I will assume you guys know that. So maybe now let's do a convolution example. So for an LTI system, guys, IO relation is given by input-output relation, remember, is given by h of t, okay, convolved by x of t. This is called the convolution integral. And let me write it openly. This is minus infinity to infinity, either h, the properties will be the same. It's either h of tau x t minus tau or x of tau h of t minus tau. So this is equivalent convolution integral. I mean, equivalently, this is convolution integral. I mean, similar to convolution sum. Okay, convolution sum, and this tau is the integration variable. Don't get confused. And you remember the convolution sum, right? Sum k, h of k. Similarly, k was that dummy variable there, x of and minus k. Remember, that's the same thing. K was the dummy variable. Okay. So let's maybe, guys, are we fine with this? It's the continuous version of the convolution sum, right? Again, we will look at properties of the convolution. Maybe let's list them actually and then do an example. Properties, let's list the properties of the convolution. Properties of continuous time convolution, the same actually as before. Of course, doesn't matter. Same as before. So commutative. So let's write one commutative. These are important properties that you should really know. So x of t convolved with another signal, h of t, we know equal to this. you guys can show this by change of variables in this integral. So this was, for instance, let's say x of tau, h of t minus tau d tau. Do a change of variables here, right? Show by change of variables. So for instance, t minus tau is, let's say, let's give another, okay, t prime is t minus tau. Then I need tau, which is equal to t prime or t minus t prime, I think. These are minus infinity to infinity. So I'm trying to see now x of t minus t prime, h of t prime, d tau is minus, right? D tau is minus d tau prime. I have minus dt, sorry, prime. But then I also have to change these integral limits, and we will be fine from there, because we will go back to the right. By changing the integral limits, I can get rid of that minus, right? This should be fine. Change of variables, so it's really minus equivalent, the minus infinity to infinity, h of t prime, x of t minus t prime, dt prime. So it's really, you see how to prove. I mean, it's easy to prove the commutativity. The associativity is also easy, but it's now you have multiple integrals. Associative property, x of t convolved with, for instance, h1 of t convolved with. I just need 3 signals. That's why I took this. And then now I know the order of the convolution can change. h1 of t convolved with h2 of t, right? Okay, Çağlar, good. Seems correct. All right. You guys saw it. All right. So this guy, you guys can also check through integrals. 3 distributive over addition. Addition. X of t, for instance, convolved with x2. Let's say maybe write more general signal names. This is really, we know that equal to, but let's write it here so that, guys, x of t convolved with x1 of t plus x2 of t. We know this is, this can really be distributed. So let's maybe just write the result. I think you guys are familiar with such rules, right? I think you guys are. For identity, it has an identity element, which is, what is the identity element of the continuous time convolution? What do you think? So we are looking at this operator, convolution operator. It's delta of t, right? Similar to before, it was delta n. So actually, then I can really have, that would mean operate or execute this operation over any signal through the identity element. It's gonna give me the same signal. So it's really not making a change. Of course, due to commutativity, you can change the order. Guys, another property is, maybe we should say, if delta of t minus t0, we've seen it convolves a signal, doesn't change it, but when its shifted versions convolve a signal, it is shifted. Maybe we could write these over. Like, I mean, this is already what we know. You can show this through the integral again, convolution integral. Let's see, x of tau delta. It should be t minus t0 minus tau d tau. Remember, these samples, this guy samples at tau equals, samples from x of tau at tau equals t minus t0, right? From the properties of the integral. That's how we got x of t minus t0. Does it make sense? Samples the signal at here, and it's an integral, so it's the sampling property, remember, of the second kind, actually. Let's see. Was it here? Properties of, no, sampling property of the second one here. You can see it samples, so now the convolution uses this property and convolving by a shifted impulse really just shift the signal. And remember, this delta actually, remember, this guy was the impulse response of delay system actually. Already we know this. So it really confirms, right, its goal. I mean, this is this delta of t minus t0 is the h of the signal of the system. X of t goes in, right, system S, delay system. Remember, x of t minus t0 goes out. So this is really x of t convolved by delta t minus t0. So for instance, if delta t minus t1 goes into this system, what happens? What is the output? For instance, you would have to say the output is the same system, okay? Delta t minus t1 convolved with delta t minus t0 shifts again, right? T minus t1 minus t0, for instance. I mean, it's just shifting whatever it sees. I mean, you can say it's really the shift amount is now the total shift amount of the two. Okay, I think we wanted to do a convolution. So let's do a convolution example. Are we clear with these? Properties are almost the same, I think, right? I mean, same as before, as in discrete time convolution. Just now the operators are becoming continuous time. So an example, calculate y of t is u of t, for instance, convolving u of t. I mean, you can think of one of them as the integrator system, and this is really the input signal. Okay, x of t and unit step function. So normally we, in continuous time convolution, we like to use the graphical method. Here, however, maybe I can just start by the convolution integral here. Minus infinity to infinity, let's say u of tau, u of t minus tau d tau, right? This would be, remember what this guy is. I just wrote 1 for tau greater equals 0 and 0 tau less than 0. So now that would mean I would have to change my, you see, integral limit, bottom limit to 0. This is 1 times u of t minus tau d tau, right? And now the same, do the same thing. This is equal to 1 for t minus tau greater equals 0, 0 otherwise, right? Now I'm trying to put that into perspective. So this will be really equivalent to tau greater, or here in this case, tau is less than t, right? And in this case, actually, this is equivalent to tau is greater than t. I mean, we can put equivalence to one of these. Tau. So actually, you see, when tau is less equal to t, we have to have a non-zero integral. So 0 to t, 1 d tau. And this is really actually showing us I have, you will see that mathematically deriving this is not as easy. We will do this as in the graphical method. We will get this. Because why did I add u of t now? Because I want t greater than equal to 0. because tau was greater than equal to 0, right? I carry out I bring over all these constraints. In the end, guys, because I'll end up with tu of t. Remember, it's an integrator system. A step function comes in, integrates, it will be a ramp function. That's why it's tu of t. But so this is a way, but I think I would, for continuous time convolution, we always like to use this graphical way where we flip one of the signals and slide it over the other to see all these here constraints of like u of t and things like that. So let's do the graphical method now. So guys, let me do the graphical method. Okay. Again, let's use this example, e.g. on this, let's say, example u of t. Let's carry out this convolution. So first formula, first graph, sorry, is this guy. I remember, the formula was minus infinity to infinity u of tau, u of t minus tau theta. We're trying to show this graphically. So u of tau, bring u of tau. We did this also in discrete time, actually. So I'm really repeating. It's, let's say, this guy, tau. You see, tau is the dummy integration variable, okay? Now, what is u of t minus tau? You can flip it. So maybe to get u of t minus tau, flip this guy, guys. Flip it. So I'll get u of minus tau, right? So it's going to be like this. Right? U of minus tau. So just pay attention to this. So let me write this. Minus tau. Okay. Now shift by t. So start shifting by t. It's going to be like this. U of t minus tau. T bar for t positive. This is for t positive. Tau. So we will do that actually. So bring that here, guys. Tau. Bring the second signal to any arbitrary t, right? So u of t minus tau. Now the convolution integral tells me to multiply them, right? Multiply and integrate them out. So I will have now, so let's write u of tau, u of t minus tau. So this guy will be really, where is it? Just look at this form of the graph. It's really here. T is somewhere here. Right? It's zero everywhere else. I multiplied the two signals. If you understand it here, continuous time convolution will be done actually. We will solve a few more examples with Fırat today to you on this. So guys, this was the first, by the way, this was the first signal. It happened to be the same signal here, but this is the second signal, okay? It can be any other signal, of course. Multiply them or take a product pointwise, multiply them. Now integrate it out. Okay, sum it out. This then it's really the area underneath, right? This was 0. So from here, I want to say, let's say this one, bring this one. It's 0 to t1. This is 1, right? The multiplied 1 dt. This is really, again, t for, actually, the area underneath is t for t greater equal to 0, 0 for t less than 0, right? Guys, this equality I can put to any size. It's a continuous time space. Okay. So that would mean this is equivalent to, this is really equal to t dot u of t, right? Again. because for t less than 0, maybe I can show also, for t less than 0, the two signals did not have any overlap, right? Because I had u of tau here, remember, u of tau, and u of t minus tau, the second signal was somewhere here, right? T less than 0. You see the product is all zeros. U of tau times u of t minus tau, product is really all 0. 0 for all tau, right? That's why in the end, this convolution is equal to t u of t. This is really, guys, so maybe let's not write here, but let's say this is what we are asking. So in the end, oh, okay, we have to add more. In the end, we have actually the input signal was u of t. This was input signal. System, it went into an integrator system. Then the output, so this was x of t, right? The output was actually t u of t, which is this guy. 0 here, and it was the ramp. Okay? This was the y of t, as expected. Integrated this input function. Maybe I think we have another one, another few, two examples. Actually, Fırat is going to solve for you. Yeah, one of them is a shifted integrator. I'm trying to see. Let's see what else I can. I have to talk about cascaded and parallel systems. Any questions until here, guys, before that? Are we fine? Somewhat. I mean, please just, these are not difficult. You have to just sit down with a pen and paper, right? And solve these. That's it actually. I think half an hour to 1 hour study would be fine every week. After the class, then you're done for the material, which is great. Guys, remember the cascade and parallel systems, cascade and parallel connections. It's the same, I mean, here with for continuous time systems, they are the same as the discrete time systems. Remember, we had, for instance, I can really talk about cascade. Recall, this time it will be really continuous time systems connected in series. For instance, n of these guys, x of t goes in, y of t goes out. What would you expect to be the overall impulse response here? Cascade or in series connection, let's say. In series connection. Overall impulse response, what is your guess? Remember from discrete time, it is, so h overall of t is h1, I think applied. Yes, thanks Evren. Yes, h1 convolved with h2, convolved with n of these, or however many. It's the convolution of all the impulse responses. You can show this actually. And you can also show, guys, these orders are exchangeable, right? Due to commutativity, associativity with all these rules. For instance, that is equivalent to really, for instance, I could say Hn of t, I'm bringing to the system, really just any order is fine. I mean, just use all of them. It's the equivalent, right? due to both commutativity and associativity. Right? You can use all those rules to really show this is equivalent. Parallel connection of systems is, remember, again, same parallel connection of systems. I can say bring an X, an input, I mean, take an input. This time the same common input goes to multiple systems. That was the idea, remember. And this could be really done for many, many systems. And H sub n T, remember, we can just add these up. And of course, there are others. And the equivalent overall system response or impulse response was, remember, you understand when I say H overall, right? This would mean X of t goes in, there is a single system. I mean, it could be multiple systems or it could be a single system, which really summarizes up, combines all the effects. I think you guys also recall this. It's the addition of all these impulse responses, right? Same as in discrete time systems. This is really something already you know of. What else? Let's see. This uses superposition. Maybe I want us to do a few examples. Maybe, okay, let's do this example, for instance, guys. Example, for instance, I have this system, X of t. So here is a system where, okay, let's see, maybe let's do it in this way. There is an S1, there is an S2. This guy has an impulse system. The system 1 has an impulse response H1. System 2 has an impulse response H2. They are connected in parallel. Okay. And here sometimes, guys, there is an inverter which inverts the sign. You have to be careful. If you see it here, it's plus. It can be also inverted. I'm not showing an extra system here, but there should be, you guys probably have seen it in digital circuits and stuff. There is an inverter here. So it's a minus connection. And then it goes through an integrator system. Okay. So this is, let's say, H3T, and this is Y of t. For instance, I'm asking you, find the overall system and determine whether it's causal and stable. So I'm asking you, what is HO of t, and is it causal, and is it stable, for instance? Okay, so I will give the form of the systems. Already you guys know what the H3 is, but H1 of t is given. H1 of t is delta t plus 1. Okay, on purpose simple systems. You see a shifter to the left and one by one time point, and then a shifter to time point shifter to the right. To the right, to the left, yes. And what is H3T? This is already given from the block diagram. It's an integrator. You guys know its impulse response. We've just studied it. What is it? U of t, right? Yes. So, guys, then overall, what is the overall? You guys will, I think, read it off from the block diagram now, right? You guys can do it. Add H1 and H2, convolve with H3. So h of t, so I'm assuming everybody can really, plus this is plus, read it off from the system. Convolve with H3T. This is it. Now let's insert the given impulse responses. What is H1 plus 1 plus delta t minus 2. Now convolve these guys with u of t, right? Actually, use the property of distributive over addition, right? Here. Of the convolution, I mean convolution, distributive over addition. So in the end, it's really u of t plus 1 plus u of, for instance, it was a minus, guys, by the way, right? Sorry, I didn't read it off nicely. Sorry. Guys, check it out. Yes, it's going to be a minus from the, there was an inverter there. You read it off from the block diagram. Minus ut minus 2. So what is this form actually of this impulse response? You can just see u of t plus 1. What is it? So let's say this is 0, this is t. U of t plus 1 would have been this guy, right? And what is, sorry, the other way. I mean, I shouldn't draw it in this way. Sorry. It should be going to the other side. Just shift it. There is no flip. Sorry. Time. No, there is no time flip. It should be here, right? U of t plus 1. Then what is u of t minus 2? Also draw that. This was minus 1, 1. And this would be the u of t minus 2, right? 2. Okay, this was t plus 1. U of t plus 1, t minus 2. Now, subtract them, right? Subtract u of t minus 2 from u of t plus 1. So actually, our overall impulse response is really what is remaining in between. It's this pulse. I mean, these were 1, of course. Minus 1 to t. So my two other questions. Now you found H overall. Is it a stable system? Remember, stability, you want to actually look at if it's an LTI system. Here it's an LTI. We're already talking about impulse responses. We're looking at the area underneath the absolute impulse response. Is it then stable? I mean, remember, you have to check this. And you have to check whether this is finite or not. Here, what is it? What is the area underneath? I mean, it's obvious, right? So it's really minus 1 to 2, 1 dt, which is really area underneath is 3. So it's a stable system. Doesn't blow up. Is it causal? For that one, you can check the form of the impulse response. Remember, actually, yeah, we've also for LTI, this was an LTI system check, right? We've had a constraint. Was this 0 for t less than 0? That was the check. And it's not, right? So not causal. Is it clear? I think probably you're fine. Perfect. I had another example. Actually, now I believe I can do a little bit more and then leave, guys, to leave the floor to Fırat. Stable and causal. Can just finish it up next time. Maybe let me see if I had other problems. Yeah, one more convolution problem. Let me solve it. This was, sometimes you don't need to resort to graphical methods. We will solve two examples where you need to resort to graphical convolution method, but sometimes you may be just fine by the mathematics. For instance, this is such an example. Let's say given, guys, h of t, the impulse response of this continuous time system, delta t minus 1 plus 0.5 delta t minus 2. Remember, convolution with a delta is easy. So if my impulse response is given by deltas, I don't need to really go to the graphical method. So I can just write, find how, and given also x of t. X of t is also given. Given x of t, it is given as given x of t, given h of t. Guys, it's given in this way, 0 and 2. Okay, maybe let's just do it. 2, 1, t, given x of t, okay? In this way, given also impulse response, what is, question is, find the output, y of t, okay? How would you go by it? Because things look like they are manageable, these signals are manageable through simple mathematical manipulations. And whenever delta, the impulse response is given, so impulse response is given in terms of delta functions, right? So if I can somehow express the signal, input signal also by some known functions, I will be easily shifting those, right? Because convolution by delta are shifts. Shifting the signal. They are delay. They are the impulse responses for delay systems. So this system is actually, you can think of, it's the addition of two systems, right, guys? And there is a scaling too. So for instance, this H, guys, is really like such a system, x of t. There is a delay system, delay by 1, t equals 1, because that is delta t minus 1. And then delay by 2, another delay system, but also multiply by 0.5, right? And add them up, right? This is the, because this will be delta t minus 2, then multiply the output by 0.5 and add them up, right? Does this make sense? Yeah. So now, what is x of t? If I were you, for instance, answer, I would go for writing x of t in terms of step functions, two step functions, right? That is u of t minus u of t minus 2, right? Can you see that? So I can write x of t in this way. So now you guys can see that y of t is really x of t convolved with h of t. Just bring the math here. U of t minus u of t minus 2 convolved with delta of t minus 1 plus 0.5 delta of t minus 2. You are using all kinds of properties of, this is equivalent system, by the way. Anyway. All properties of convolution. Here it's distributive over addition, right? So I would have, let's write it all, delta t minus 1. Okay, first of all, I could have kept this as x of t actually, but anyways, yeah, let's, one way, other way to write it would have been that way, but it should be u of t, by the way. Or I was gonna say convolution, but let's write the final thing. So it's going to be u of t minus 1, right? Plus 0.5 u of t minus 2 minus u of t minus 3, right, guys? Plus or minus again, minus 0.5. Let's just minus 0.5 delta t, u t minus 4, okay? So this would be the, then if you plot this, also equivalently, guys, equivalently this is just leaving x of t here. It is x of t minus 1. I mean, do the convolution of x of t by this delta function. T convolved by delta t minus 1 plus 0.5 delta t minus 2. So it will be x of t minus 1 plus 0.5 x of t minus 2. Maybe it may be easier to go from there to the graph. So plot this. Or it could be other way around. It's fine. But I think this would be probably easier. Maybe let's do it in this way. X of t minus 1. So guys, x of t minus 1 is shifted x by 1, right? 1 to 3, 1. This is x of t minus 1. Now, have 0.5 x of t minus 2. That would be really here, 2 to 4. It's 0.5, right? This is 0.5 times x of t minus 2. Now add them up, right? That would be the, so add them up. Let's say plus, I won't fit it here. We can probably fit it to the, let's say, so a new page, let's do it. So in the end, probably we should have done it here. But anyways, so we will have this, guys. 1, 2, 3, 4. It's all mathematical manipulations, you can see. 1, I need 0.5 and I need 1.5, I think. That's too high. We should have it somewhere here probably. 1. Okay, it would be this form, T. For instance, I mean, this is really coming from the previous page. Okay. I think I'm trying to see. I will myself give you an exercise. If you can't solve it, I can solve it next time. Solve this, please, homework for your own sake. X of t, we can take a look if you want. Tell me, but you should work on it. Two systems in parallel, in series, sorry. H1t, H2t, y of t. There is an overall system response I can talk about, right? And I will give you these two, H1 and H2. And again, I will want you to find given H1 of t, which is equal to a little bit mathematical manipulation, guys. 1, 0 otherwise. From here, write H1 as, for instance, e to the minus 2t times, just for your easy manipulation, I would write it in this way, right? Does it make sense? You see, we're using these functions as extractors of some certain duration of the signal. Because this guy is really this, right? So it acts as a windowing signal. This is typically what is called a windowing signal, right? Makes sense, I think. And then H2 of t is given. It's a differentiator. Remember, differentiator, we wrote its impulse response in this way. Differentiator. So that would mean when you see this actually, y of t is really d by dt x of t, right? So my question to you is overall system. So first calculate overall system, of course. Again, just find causal and whether it's causal and stable. Of course, my goal is also first you find HO of t and then decide whether it's causal and stable. So plot also, find and plot HO of T, okay? This would be, I think, a good exercise for you. Let me see what else. Okay, I was looking at interchange. Okay, so fine. I think this should be fine for now. Any questions until here? We could give a break, okay, and then continue with more examples in the graphical method.
It's okay, right? Now it's recording. And in this question, we were asked to find the convolution of xt with itself. And to do so, as you know, we got the equation. Just yt is equal to x tau xt minus tau t tau. First of all, we will make this axis as tau, and it's again, and we got one xt, and we need to shift the other one. To do so, and I think we can. Okay, we got this one, and we need xt minus tau, and as you can see, if this part is t, this part will be t minus uppercase t, since this has length of big T. And as you can see, for the first case, this is the first case. What is it? Until T counts 0, and we don't have any overlap. So let me. And it is a case one, and it's when you can check that from that part, when t is less than 0, we don't have any overlap. Up until that overlapping part, so we can say that. And for the first case, we got t 0, and this means yt is 0, 2. And as you can see, we have started to have overlapping part. Let me draw that part with another color. Yes, I think it's better. And we have overlapping part as this part, and it's t minus big T. And as you can see, they both have 1. The 1 times 1 becomes 1. But let me first find boundaries. T minus big T is less than or equal to 0, and so t is less than or equal to 0, and t is greater than 0. T is greater than 0. Pardon me, this must be t. Okay, t come 0, and we can do it like this way. The equalities can be that way. By the way, it doesn't matter what, can do it like that way. And this is our boundary. But what are the boundaries of the integral? As you can see, the overlapping part starts when it's from 0 to t. So let me write the integral. It's 0 to t, and 1 times 1 d tau. It's tau. And as you know, the integral of 1 is tau from t to from 0 to t, and this part will be the solution of this integral will be t. Okay, and this is case 1, this is case 2. Okay, we can continue with another color. And
İlkinde kesişim olmadığı için 0 mıydı? YT eşittir demiştiniz, orada boş ya karşısı.
İlkinde evet 0.
Ha, tamamdır.
Hı hı. Teşekkürler. Devam edelim. Bu şimdi diğer bir case'e bakıyoruz arkadaşlar. And then we will continue with the third case. It's this one. When we go beyond to rectangle. And again, this part is t. And this boundary is t minus big T. As you can see, we can say that. Let me first. The third boundaries are when t minus big T. Pardon me. T. By the way, may I? Yes, I think it's better. T minus big T is bigger than or equal to 0, and I think you can see okay. And as you can see, T is no, not that part. Pardon me. T minus big T is less than T big T. Let me okay. T minus big T is than T, and T is greater than big T, and T is greater than big T. And if we rearrange this term, T becomes, I think we can say that one, right? Okay. And then we should determine the boundaries of integrals. As you can see, it's from T minus big T to big T. And again, it's 1 times 1, 1. T minus big T to T. 1 times 1, D tau, and it's again tau from big T to T minus T. And we got big T minus T minus T and 2T minus T. And we got this part, we can give equality to that part. Okay. Okay. And for the last region, we can say that when there is no overlap, pardon me, when T minus big T is greater than big T, and it comes again, our result is 0 as that part, and yt is 0. And if we combine all of it, let me choose the it's 0 when t is less than 0. It's again 0, t is greater than or equal to 2 big T. It's t when it's in this range, and it's 2 big T minus T when it's this range. Is there any question? You can brush instead of answering. Okay, okay, okay. You're right. Sorusu olan var mı arkadaşlar? The first brush is better, I think. Okay, which one is it? I think it's marker. Or the pencil. Yes, Google Jamboard can be used. But sorusu olan var mı arkadaşlar? Konvolüsyonla ilgili, soruyla ilgili. Is there any question? Everybody got it right or no? Yes or no? Can admit. Yok mu soru arkadaşlar? İkinci soruya geçelim o zaman. Geçelim mi? Should we continue? Okay. Okay, okay, but before that, I think we should stop sharing. And let me first. Okay, and it's quizin süresini ayarlayayım arkadaşlar. Sanırım biraz aşabiliriz. Okay. Then we can continue with the second and last question. And let me open a new page. Okay, good old friend. And for this question, please do it together. If you can you see a blank screen, right? Page. Okay. Then our question will be, it's not there. And it's HT is defined as e to the power minus t times t and xt is okay. And you were asked to find yt, which is the convolution of ht times xt. Okay. What should I do? No, Hasan İsmail. Şu an soru çözüyoruz. Quiz'e daha 10 dakika var yalnız. Okay. As you already understood the previous question, what should I do first? What will you do? And help me to solve this question. Evet arkadaşlar, ne yaparız önce? Ne yapmalıyız? Okay, what? Okay, Mustafa Oğuz. Thank you. But why it is so? Okay, I will first draw the HT. Okay. It's got like this. Tau, and it's h tau e to the power minus tau u tau. Okay. What will I do next? Evet, şimdi ne yapacağız arkadaşlar? Yardımcı olmak isteyen yok mu? Okay, I will.
Yerinde çizeceğiz. Arada hangileri kesişiyor bakacağız, öyle değil mi?
Tamam. Aynen öyle ama nasıl çizeceğiz diğerini?
Diğeri neydi bu? Bunun adı neydi bu şeyin?
Birden başlatacağız sanırım diğerinde mi?
Ama onu bir de şey yapmamız lazım mı? Şey versiyonu çizmemiz lazım. Şu şekilde. Değil mi? Demin de onu yaptık. Şöyle bir shift'leyip onu güzelce bir şey yapmamız lazım. Onu da çizeyim ben bir.
Birden başlayan birim
Aynen. Aynen ama onun diğer tarafa yansımasını çizeceğiz ya. Şu şekilde olacak sanırım. Gerçi bu da şeyde şöyle. Şöyle. Okay. This is t minus 1. Okay. Do we have any overlap in this part? Obviously, we don't have any. By the way, guys, I think communicating is important. So I asked the question for that part, but I can solve it. And up until t minus 1 becomes 0, it can be said that for that part, and t is less than 1, and there is no overlap. Overlap, and then the yt becomes 0 for that part. Okay. And for the second part, what do we have? And for the second part, I have overlap. And what is the overlapping region? This part, right? And when it happens when t minus 1 is greater than or equal to 0, and t, okay, I think I need a bigger size, okay, is 1. Okay, and we found the boundaries, and then we need to calculate integral. Then we are good to go to quiz. Okay, I got from 0 to t minus 1. From 0 to t minus 1. And first one is, this one is 1. The other one is e to the power of minus 2 d 2. And if we calculate this integral, we got minus e to the power of 2 and that part. If we plug the values, we got minus e to the power of that part, and we got minus part here, minus e to the 0, this one is 1, and this becomes plus, and we got 1 minus e to the okay. We found it, and we can conclude today. As you can see, we got 2 regions for yt. It's 0 when t is less than 1. It's 1 minus e to the power of minus t minus 1 minus t minus 1. It's this part. Is there any question?
İkinci şıkta integralin sınırlarını neye göre belirledik?
Şöyle belirledik. Overlap nerede ediyor? Nerelerde ediyorlar? Şuradan bakıyoruz soldan. İkisinin overlap ettiği sıfırdan başlıyor. T'den t-1'e kadar gidiyor.
Anladım.
Bunları alıyoruz. Başka sorusu olan? Is there any question? No. Yes. No. Okay, guys. And we got 3 minutes. Okay, let me pause recording.